My name is Ying Li. I'm from the ISOM department and finance department in the business school here at HKUST. And it is really my great pleasure to introduce today's speaker, Professor Xiao-Li Meng from Harvard University. Professor Meng is the Dean of Harvard University Graduate School of Arts and Sciences and the Whipple V.N. Jones Professor and former chair of statistics at Harvard. And Professor Meng has received numerous awards and honors, including the 2001 COPS Award, which is really the most prestigious award given by 5 statistical societies to one statistician annually, being the outstanding statistician under the age of 40. And more recently, he also received the inaugural P.L. Xu Award for distinguished achievements in research and education by a statistician under the age of 50. And Professor Meng is also known as a very dedicated and energetic leader in statistical profession. And he has served on the editorial boards for actually almost all the leading statistical journals. And for his services and contributions, he has received many distinguished service awards from various professional societies. So today we're very happy to have Professor Meng here speaking about statistical paradises and paradoxes in big data. So welcome, Professor Meng.
Can you hear me well? First of all, thank you all for coming here. I was told this is during the break, so I'm very pleased to see all of you. But I do have a question to start with. How many of you have taken one course in statistics? Raise your hand. One, just one, okay. No, I don't mean it, at least one, not just one. At least one, okay. Now don't put your hands down yet, okay. For all those, how many of you did well? Okay, well, all right, there's still a few. Okay, so for those of you that who did well, I hope you will be able to understand the whole talk. For the rest of you, that if you can get some key messages, I'd be very happy. This talk actually, part of it will be a little bit technical, but I would do my best trying to make it as understandable as possible. I actually will be giving you really 2 parts, and I decided last minute to add on this part. I was giving this talk, exactly the same talk, about 2 weeks ago at Seattle. There was a joint mathematical meeting. The American had this big joint mathematical meeting. And the 2 mathematical society, one is more doing more research, the other is more pedagogical. They asked me to give a joint lecture on sort of what's going on in statistics. Because these days, as many of you probably know, the big data has become so popular, data science, so the mathematicians want to know quite a bit about that. So what I decided to do then is to add a little bit on top of my regular sort of more research-oriented talk, which I'll give you in a minute. I decided to add a little bit about what statisticians have been doing in terms of a big data, just sort of give a general introduction. Now, I do think that we probably have a very mixed group here as well, right? We're coming from multiple departments, multiple schools, so I thought this might be appropriate. So we will see. And this talk, I actually, thank many of my student colleagues, friends, but you should always remember to thank your people who dislike you, because these are the people who keep you on your toe. These are the people who will make your argument as rigorous as possible. So don't forget it when you do research. Always think about these people who will be very, very critical about what you do. As some of you probably have seen, that because the talk was in Seattle, I was trying to find something related to Seattle and related to big data, just for the fun. And I was able to find, and if you know which movie is this, right? Sleeper in Seattle, and there was a quote said, well, it was a million tiny little things that when you add them up, it might be too small, so let me translate for you. When you add them up, you got big data. Okay, so it's actually not entirely wrong that what so what is big data, right? Big data, it's a phrase people use. Essentially, you collect many, many data points and typically collect from many, many individuals. So each of us is like a tiny little thing. But when you accumulate them, you will get a lot of them. My talk actually, as you probably see, that I purposely put big data in a sort of small font. My talk is actually trying to give you a warning that big data are not that big if you take into account the quality of the data, not just the quantity. So I'm going to show you, essentially I have two parts of this talk. The first part I want to show you that how the quantity and the qualities are related. I'm going to give you one statistical formula, okay? Don't be afraid of the formula. It's actually a very simple one. Every one of you should understand that formula. Otherwise, you shouldn't be here. But we will see that, okay? The second part I want to talk about how people have been using big data to really solving problems that actually itself is very small, is called individualized medicine. It's about individuals, individualized education, individualized medicine. So in the end, on one hand, you have a huge data set. At the end of the day, you want to predict something about you. And that is very tiny. It's only one person. So that's essentially is the two things that I want to talk about. But let me first explain the title. What do I mean by paradise, right? For any educators, for any professors, for any deans and colleagues here, that a paradise to us is that whatever you're studying, there are many, many people want to study. Okay, there are many, many people come to the field that you're working on. So for me, as a statistician, I'm most happy when I see there are a lot more students want to study statistics. Now, not necessarily they will become a future statistician. So I'm talking about general pipeline. The idea, that's why I was asking how many of you have taken at least one course in statistics, right? It's a sort of a basic knowledge. So what I'm showing you is this picture of, this is the number of statistical concentrator, that's Harvard's word for major, in my department over the years, okay? So I'm going to show you what this picture is. We typically, up to like 2006, 2005, we have, all 4 years is only a single digit. Very, very tiny. Somewhere starting from 2006, 2007, it started taking off, okay? And in fact, this curve was fitted around 2010. So you see the shaded area? That's where the prediction was. So we were right there, and we fit the curve. And when I fit the curve, when I present to people, people saw that I made up the data because these points fit the curve so well. You see that? That's the exponential growth curve. And that exponential growth rate, can you guess what the rate was? It was 60% every year, right? If you have stock 6% every year, you won't be sitting here, right? You'll be so rich. So at the time it was 2010, and we were predicting the future. How many more you'll be having, right? Okay. So by the way, this itself is a statistics already. Okay. This is a statistics. Now, what I want to show you is the following. So as you predict, you see these bars, right? For those who have taken one course in statistics, you know what these bars are, right? How do you calculate these bars? Anybody still remember? These are called a confidence interval, right? Okay. Most easy ones is plus minus 2 standard deviations. But these ones are actually a little bit more complicated. You will see they are not perfectly symmetric, as they shouldn't. Okay? You do transformations, you do all sorts of stuff. But whatever it is, there are these bars. Now, when I was going to present this, I saw that I'm not going to refit the data, because now we actually have more data. I want you to see how well was the prediction then, and how important it is to have the bars, okay? Imagine, I was a department chair. I need to plan for the future about how many more faculties we need, all sorts of things. So the prediction is important, right? Okay, so let's see what happens in 2011, okay? Pretty good, okay? You see, first, it deviates from the exact point estimator, but it's within the bar, right? See the important bar? Okay. Now, in real life, if you really want to predict the future, you need to refit the curve, taking into account this new data. It's going to lower a little bit, okay? But just to illustrate how hard it is to predict long term, not short term. I'm going to stay with that curve and show you the next one. Still pretty good, right? Now again, you probably should refit the curve. You probably will be seeing something should be along this line, okay? But I'm going to continue, see what happens. See, these bars are good bars, you see, right? I mean, this is really testing real-life statistics, okay? This is not any simulated models, you know. I was debating with my colleagues. My colleague would say, no, okay. But now by this time, you will see probably the rate is pretty clear where it goes. It's not going to be here, right? Okay. Now, I want to ask you, now we have last year data, okay? I don't even have a bar for it because we didn't predict that. Okay, well, let's see what happens. Uh-oh. So that's the growth, okay? So you see a small illustration about the usefulness of these curves. These are not exactly mathematical prediction. If you just do mathematical prediction, you're not going to give the bar, right? You fit the exponential curve 60%, but you will be pretty off. These bars are important, okay? So now the reason I emphasize this, both to illustrate that this is what we call the paradise, because for us, there are so many students coming to study some statistics. Vast majority of them will not become a statistician. We are actually much happy about that. We want people go out to have some statistical knowledge, even for reading some chart like this, right? Someday you become a department chair, department dean. Somebody predict these numbers, you'll be asking, where's the bar? Right? If you never study statistics, you may not ask the question. You want to ask where the bar is, because without the bar, you could be very off. Okay? Is that clear for the students? All right. So what are the other part which is really good? Well, statisticians these days that we can have a much better airplane, taxi, party conversation. What do I mean by that? For those, I have statistical colleagues here. We all know that it used to be the case. If in a party or in an airplane, people asking me, like, what do you do? If I say I'm a statistician, that's the end of the conversation. Right? I mean, truly. Now, either it's the end of the conversation or people say, oh, I hate that course. I used to take statistics and I did so poorly. And I don't blame people because most statistical course, my colleagues know, we used to teach in such a dry way, right? We teach all the, for you still remember, 1 sample test, 2 sample test. There's no 3 sample test, okay? And we just go on and all the different curves, and so it's sort of dry with many of people who have no interest in statistics, right? And let me tell you a really interesting story that, to a point that or loved ones or a spouse that have very creative ways to explain what we do sometimes during these parties. So I want to tell you the story that told to me by Professor Peter Donnelly. Some of you may know him. He is a really well-known statistical geneticist, and he's currently at Oxford. I overlapped with him at the University of Chicago at the time we both were teaching. And he gave the following story that because he studied statistical genetics, right? He does a lot of statistical modeling. And so at these parties, people will be asking his wife, say, what does your husband do? Okay? And her answer would be, he models. Get it? Model is like a modeling, It's not a statistical model, it's like the model. Then of course people, his wife's girlfriend gets very intrigued because they would be asking her, so what does he model? His answer would be, her answer would be genes. There are 2 different kinds of genes, right? The genes you wear, and there's a genetic gene. So it's a very creative way answer these questions. We don't have to do that anymore. Now if you say, I study statistics, you say, oh yeah, big data or data science, so on and so forth. Now actually the problem is the other way around. When we think about all these big data, like what do we really know about them, and how they really help us to make the decisions, and that's a part of my talk I want to emphasize. But this is really also a golden era for methodological research. Okay, I'm going to show you a little bit about the type of research that I'm engaged in. But before I do that, this is also, there are really some foundational issues. It's just not the sort of a methodology like implement through computer or through software. There are lots of very theoretical questions, even philosophical questions, which I'm going to raise one by the time we talk about individualized medicine. Okay? So I want to sort of give particular students a sense that statistical research is really a very broad one from the philosophical question, which I can already ask you that I don't know if any of you, not any of you, some of you have thought about what makes possible for us to predict future? Like the one, what makes possible, future is something, well, there got to be some connections here, right? What it makes possible to predict future? That's really a fundamental question for statistics. It's a philosophical question to all the way of the real applications. So because I was trying to give people a sense of what statisticians have been doing, so I'm going to just give you the next two slides. Essentially, is not about my work; is about what statisticians have been doing. And I want to start with Berkeley's group. Okay. And I choose this group because they have been doing very well integrating statistic probability with computer science, machine learning, information theory, and mathematics. I'm going to give you just a little bit example of the type of problems the professors there are working on. And they're really trying to use that to connect, I think that you come from a variety of fields. Some of the example might relate to you better than others. Some of you may know that Professor Michael Jordan now currently this is not the baseball player, okay, but basketball player. This is the Michael Jordan. He is now the department chair of the Berkeley Statistics, and he has 50-50% joint employment between stat and the computer science and the Martin Wainwright. Two of them had been doing really fundamental works on this problem. Among many others they work on is this fundamental trade-off between what I call statistical efficiency and the computational efficiency. What do I mean by that? For any of you, if you have ever done these type of research or have done these studies, you know there's a following phenomenon. There are these methods that you can compute them very quickly, but they're not very good. Their statistical errors are large. Like, remember we talk about these bars, these intervals? There are these quick methods that probably give you a very, very large bar, okay? So you want statistical efficiency, you want the bar to be as small as possible, but it still had the right coverage. If you say it's 95%, it should cover 95%. All right. But you can make it much larger. It will be still at least 95%, but it's not that good, right? So the trade-off typically will be the following. The method itself will be easy. Those methods tend to be easy to compute, like very fast, tend to be statistically not efficient. On the other hand, there are these methods that will be statistically much more efficient, but computationally will take like half hour or a day or even a week. So the question then is, how do you trade these two things, right? Would I be willing to spend another half hour in order to gain another, say, 10% of statistical efficiency? Maybe I do, but I'm not going to spend another week in order to increase 10%, right? So where do you make that trade-off? How do you mathematically formulate that? That's not easy at all. Okay, so they use this decision theory, have been working on that. Professor Bing Yu used really all the statistical machine learning theory, including signal processing, and she has worked on many of those problems, connecting with the engineering side, the signal processing. And Mark Van der Leer has been using what people call this target learning, which is use the traditional, in statistics there, it's called a parametric, semi-parametric theory, which is, I'm not going to go into detail, but the idea here is that using these well-studied statistical theory, come up with sort of a new way of dealing with these really big problems. And here is Ben Stumfel. He's actually a professor of mathematics doing algebra, but he's a pioneer of what they call algebraic statistics, which is really a pretty new branch. Is trying to use these computational and combinatorial techniques, study these statistical hypotheses and other calculations. So this is the one example of one department or one university has a lot of leading researchers integrating a variety of sort of mathematical science related areas to do the big data. Another example I want to give to you is really another group of people. This is cross universities. I'm part of this group as well. And we have a sort of internal joke here. We call it BFF. BFF also stands for best friend forever. This is the kids use. And the reason we use that is inside the statistics, there are really three major schools, the Bayes, frequentist, and the fiducial, and we always sort of argue with each other, so we want to sort of unify this theory. I'm not going to get into the detail here, but just to say that what this group have tried to do is something we call the fusion learning through this concept of confidence distribution. Remember, I give you the bar, which is the confidence interval. Confidence distribution is just a way to accumulate all the confidence intervals, 95% and 96%, 97%. You put them all together, you can come up with a distribution. The reason we do that is this is from Rutgers, from University North Carolina Chapel Hill, UC Davis, Purdue, Missouri, University of Illinois, Chicago, and Stanford, is that these days, because you have all these big data, and because the problem is too big, you will have various groups that everybody studies apart. In the end, you want to combine them. Right? This is what we call the fusion learning. This is one example that there's a variety of methods which may or may not mean much to every one of you or some of you. Let's say you have different studies. Each one come up with some kind of distribution or like confidence distribution. Some using, say, Fisher's exact method. Some using bootstrap method, some you may have heard about. There's a Bayes method. At the end of the day, if you have a variety of study, they based on different data set, but they're all trying to study the same thing. How do you combine them? How do you combine them to get one conclusions? And the difficulty here is not just the methodological difficulty, is these distributions, for those of us who study these different perspectives, they were really constructed using very different perspectives. So they all look like a probability distribution, but they have entirely different meanings. Some are frequentist distribution, some are posterior Bayes distribution. These are all different distributions. They have different meanings. How do you combine things with different meanings? It's like combining apples with oranges. So how do you think about those things? So these are the type of problems that we work on. So now let me switch to the ones. Let me see if I can get out of here. To that more technical aspect, and I'm going to explain to you. Let's see if I can get this right. So this is that was really an add-on to for that general audience, and so the talk I'm going to give, I'm putting together a paper specific for this talk, but the material I'm using is really from these, mostly from the first paper, and there's no Nobel Prize in statistics. This is just trying to get people's attention. Okay, and there's the more technical one. Is on the Simpson paradox, which I'm going to explain. A lot of material is from here. There's a general review paper called, we'll talk about this sort of individualized treatment, is coming out in the annual review of statistics and its application this year. So let me just go, this part I already talked about, but let me give you specifically, now I'm going to talk about the type of research I'm doing recently. There are three kinds of big class of problem. I call them multi-resolution inference, multi-phase, and the multi-source inference. In this talk, I'm going to touch on this one and this one. Okay, not talking much about a multi-phase, but I'm going to give you a specific example to illustrate what do I mean by that. And in terms of foundation of statistics, these days, what I think what's important is to really have a paradigm shift, not thinking about much about a quantitative consistency. In statistics, there is a whole theoretical framework called consistency, right? We prove things are consistent in the following sense. If you have more and more and more data, eventually when the size of data goes to infinity, you will be getting exactly right. That's called a consistency, okay? So that's a good criteria. Except that there's one big problem these days, that the data you have that theory, which I just said, is based on the idea that you'll be taking a sample, taking a random sample, taking a representative sample. But these days, you have online data set. Let's say half of the population give you the data. You have no idea whether that's representing the whole population or people, some people just like to say anything. Some people like to report in a very biased way. So you really have no control of the quality. And when they don't have no control of quality, this consistent theory no longer really works. So what I've been thinking about more is the qualitative consistency. What do I mean by that? At the end of the day, is like whatever the data, whatever conclusion you got from a study, do they change your opinion? Do they change your decision? Let's say this is a doctor needs to learn about a lot of medical evidence, the clinical trials, all sorts of evidence. At the end of the day, is say, does the evidence he or she have will change your treatment? If they give you the same treatment, the statistical answer could be very different. But as long as they give you the same treatment, I would say they're qualitatively consistent. You see my point? Okay? It's a way trying to get around this issue. I'm also trying to emphasize more about relative optimality versus the absolute optimal. Optimality, as anyone study mathematics, applied mathematics, statistics, there's always these procedures that we're trying to establish to say they're the best that you can use. Okay? But the best is always under certain assumptions. There's no such thing as absolutely the best. But although mathematically we formulate most like that, I think we should emphasize really a lot more about relatively optimal. It's basically saying my method is better than yours. Now, both of our methods probably could be very bad. But given the circumstance, given the time resource, given the money resource, this may or may not be feasible to do even better. So it's the relative optimality is really matters. Okay, now let me give you a specific example that I was involved, and to illustrate this whole concept of these three sort of multiple, aspect of inference. So this is a project called On the Map, and is conducted by U.S. Census Bureau, and you can Google. Google works in Hong Kong, right? Okay, sorry. That's fine, okay. Because I had trouble in China when I say Google, people look at me, so you can Google. What I want to do is the project called the Local Employment Dynamic. What I want to do is very cool, okay? They have this data set online. You can find it, and you can try to study, say, who are the people living in my area? What are the people living in my area? And where they go to work? Okay? Or you will say, okay, here in this area, there are all these companies. Where, people working in these companies, where do they live? Where they come from? How they commute every day, right? So the idea here is this is an incredibly rich data set for people to study all sorts of economic relationships, transportation, design, all sorts of stuff, okay? This is what the U.S. Census Bureau put out. So what they call it's a paired employee-employer information. And this data set was, how did they do that, right? This seems like a very complex problem. This one was they put together 20 different kinds of data source, okay? This is the one big feature of this big data. It's not a one data source. It's a many, many data source. And they have all sorts of different quality. I'm going to focus on that in a minute. So what do I mean by multi-resolution, which is quite clear, right? Supposedly, you can zoom in, just like a Google Map, right? Google Earth, right? You can zoom in any region. For example, this is Las Vegas. I know some of you probably have been there, right, to Las Vegas. Hope you didn't lose too much money. Now let's say you zoom into this, there's a famous Las Vegas, strip. You zoom into here, and you see the people live here, and then you figure out where they work, where they come from. So, and the idea is this is all over the U.S. that you can zoom into any regions. Okay, so this is cool, right? You want to do that. Except that there's a problem, right? These data are, when you only have few people live there, only few companies there, that you have issue of confidentiality. People don't want everybody to know, where I live, how I travel, right? You want to have this sort of statistical information, but you don't want to invade individuals' privacy. And this individual here is not necessarily just the individuals. There are also companies. Companies does not want to disclose all the information, right? So how did they do that? Well, you might be surprised. So this is really as I said, this is really the multi-resolution. Resolution is like taking pictures, right? You zoom in, zoom out, okay? So I want you to keep in that mind because that's an important concept that I will talk more later. Okay, so it turned out that the data you will see online when you go to this site, okay, everything you see, they're not real data. They're simulated data, okay? Now this is part of most people don't understand. Like, if you're an economist, you're a sociology, you're going to get all the data, you analyze them, but don't forget that these are actually not real data. These are synthetic data. Synthetic data is just a fancy word. Somebody made them up, okay? But they made them up in a sort of statistically meaningful way. And what they did was actually really interesting. For those of you who know a little bit about the Bayes theorem, Bayes statistics, they actually construct a statistical distribution, relate all these things together, then they simulate it from that distribution, okay? And the process is actually a long process from data source, and so this is what they call the multi-phase. Multi-phase means that this analysis is not done by one person, not done by one team. It's done by multiple stages. And in fact, more complicated than that, every stage may or may not talk to the next one if they have confidentiality constraints or because the problem is too big, okay? Now we're talking about statistical inference for which that I only have partial information. Somebody worked previously, clean some data, give to me. I do something to the data, I give to the next person, go on, okay? And then you see the problem there, trying to do mathematical modeling to make sure they are all coherent is not easy at all. Finally, what do I mean by multi-source? And I want you to really pay attention to this one. This whole thing, when they're trying to build this whole model, because they require a lot of data, right? They require like employee data, employer data. They actually have 20 data sources, okay? They have something, it's sample survey, right? Sample survey, probably most of you, if you have taken statistical course, you should be familiar with. This idea is that you're using probabilistic design to randomly choose from a population, right, in order to study the whole population. Now, this design is they take 60,000 households from the United States. Now, this sounds very large, but because the United States has a lot more, there are lots of households. So that represents essentially 0.05%, okay? So that is a tiny sample. Got it? Okay? It's a tiny sample. Now, but it's a tiny sample with very good quality because it's purposely done by Census Bureau, designed it, okay? What's the next data? Next, they have this administrative record. For example, they have unemployment insurance coverage, wage record, that covers 90% of the US population, right? US has about 320 million people. 90% is a lot of them, right? But that data set was not collected for statistical purpose. It was collected because it was required by law, right? And then that data set, as we know, that data set is a biased data set. What do I mean by bias? For example, all the federal employees are excluded from that data set. So you know that cannot be representative, okay? So here you already have a situation. One is a tiny sample, but with high quality, right? And then this one is a huge sample, 90% of the population, but with unknown quality, okay? Then, as I said, this is never intended for inference purpose. Then you also have like census data, which they try to quality data. They're trying to get all the data, the earnings, the wages, which covers 90% of the US jobs. So you have this variety of data sets. They were collected for all different purposes. Some are high quality, small. Some are low quality or unknown quality, but very large. At the end of the day, how do you combine all those things together to come up with something meaningful? Is that clear? Is that clear what the big problem is here? Okay. So now I'm going to focus on, in the next probably 20 minutes or so, trying to get through this part. I'm going to show you how small a big data is if you do not pay attention to its quality. Okay? So big data often, when people say big, they are talking about big in terms of size. Is that clear? Quantity, not quality. Okay? So this was the question posed to me by Jeremy Wu, which is the project manager for that project. He asked me about, he told me the following, right? He said, we know, statisticians know, for many, many years that if you have a 5% random sample, it's better than a 5% non-random sample in measurable ways. We can mathematically show, we can through simulation, we can do mathematical to show it's a better sample, statistically. It has a smaller bias, suppose it shouldn't even have any bias, it has more predictive power. But that's comparing 5% random sample with 5% non-random sample, okay? What about the following? So this was the question that he asked me, say, but what about comparing 5% random sample with 80% non-random sample? Now, I want to see a show of hand. How many of you would trust that 80% non-random sample, and how many of you would be trusting the 5% random sample? So let me first ask, if you trust more the 80% non-random sample, raise your hand. Okay, we'll see a few. Okay. If you trust the 5% random sample, raise your hand. Okay, this crowd prefer the smaller, better quality. If you say, I have no idea how to answer that question, raise your hand. And these are the right answer. Right? Because, think about it, because when I tell you 5% random sample, you know exactly what I'm talking about. You shouldn't know exactly what I'm talking about. It's a simple random sample. It has quality control. When I tell you 80% non-random sample, you should ask me, like, how non-random is non-random, right? If it's very close to be random, 80% should be good. If it's terribly non-random, then it may be very bad. So the answer should be depends. Now, one lesson you should learn, anytime you do not know how to answer a question, say it depends, okay? And most time, you will get it right. Okay. Now, but what about 90%? What about 95%? Well, I say I still don't know the quality, right? I'm going to increase the percentage. Let's say, now how many of you, if I tell you I have 95% of the population, and I want to estimate the population average, okay? And the other is 5%. Now, how many of you would trust the 95% data? More, right? How many would still say it depends? These are smart fellows, okay? Well, now you'll be thinking about, wait a minute, Xiao-Li, if you keep going, like if you get 100%, then obviously we should trust 100%. 99%? Come on, I mean, if you have 99%, I better trust the sample, right? Okay, well, let me show you how to think about this problem and how to do these calculations, okay? And how do you quantify? So here's the research problem, right? I was given this problem by Census Bureau. And I thought, oh, very interesting. People actually haven't thought about that question. I mean, we always think about, me even as a professional statistician, I would say, oh, 95%, 99%, that should be good enough, right? I mean, how bad it could be until I do the calculation. So I'm going to show you my calculation. The most important thing I'm going to tell you here, particularly for students who are looking for a research project, most of these researchers is not about getting the answer. It's about formulating the problem. It's once you formulate right, I will show you how simple it is. Today, all I'm going to use, there's no calculus. All I'm going to use is simple arithmetic, okay? But only after you know how to formulate it right. Okay, once you formulate it right. So the basic thing here is, how do I find that index to index the quality? I have an index for quantity, which is sample size, right? Count how many people. I have a clear index of the quantity.
But what is the index of the quality? How do you think about the quality index? Okay, I'm going to show you what that is. And then once you have that, I can show you the calculations. Okay. Then most recently, this paper coming out, I was in Seattle, as I told you, just by coincidence. The joint statistical meeting last year was in Seattle as well. In August, I attended the meeting. And then there's a Professor Tom Ruiz, who has actually worked for Census Bureau as well. He posed an even harder question. He said, OK, which one should we trust more? A survey with 60% response rate or a non-Propertics data set covering 80% of the population? That's an even harder question, right? Remember, the question here is a non-random sample versus a random sample. But even for a random sample, a survey, you ask people, not everybody answered the question, right? So then that becomes 60% of that random sample. Now, because people not answer, everybody answer, the quality no longer is controlled either. People can self-report. For example, people tend to not report high income because they have not paid the tax, right? Okay? So now how do you compare a sort of self-reported huge data set in a population, 80%, and here is something that well intended to control quality, but because people did not respond, you have a deterioration of the quality. How do you compare these two? Right? Even harder. Okay? So now I've teased you enough. Now I'm going to give you the next two slides, a little bit technical, but I promise you that the notation here, but there's nothing here go beyond a simple arithmetic. Just the notation. Okay? Imagine the following. Imagine you have a population. Let's say N here. Let me take the United States because this is the example I'll be using. Let's say N here is 320 million, okay? Each individual. Let's say we're doing these X are 0, 1s. Let's say we're talking about elections, okay? Let's say X equal to 1 if the person is going to vote for Donald Trump, okay? And the 0, vote for someone else. Is that clear? For Donald Trump, he wants to know how many people will be voting for him, right? Okay? You'll be surprised how many people vote for him. But so the estimate, which is the quantity one estimate, will be average of all these x. Now I'm writing a more generic form and say there's a function of x. It does not have to be just x. It could be something else, right? But think about gx is just x. So if you average of the 0, 1s, you get the percentage, right? So this is in the population. It's a number that we don't know, okay? But what we do know is we're going to take a sample, or we probably look online, right? Suppose somebody now put on an online survey, okay? Say if you vote for Donald Trump, put on 1. If you don't vote for Trump, put on 0. Now online survey, you have no way to control the quality. You don't know, because then, whoever wants to answer, somebody probably just trying to mislead the audience, right? So you have no control whatsoever. Okay. So here's a technical thing I want to tell you. Okay, so what I'm going to do is that I'm going to take this R equal to 1 if this X value will be reported. If it's 0, it will not be reported. For each person in the population, they either report that value or they don't. Okay? So there are two values here. One X is the value. If they report, that's their value. R is just indicated what I call the recording behavior. Okay? And I used R because it's not only just recorded, self-reported, responded. It's turned out to be all hours, so I do that. Okay. So what do I observe? I don't observe X for everyone. I don't observe X, but I do observe R, right? Because I look at who reported. Other people reported their R is 1. People don't report R is 0. Okay? But I'm not going to assume that R is random. In the probabilistic sampling, R is random, right? Because we decide, we flip a coin, you're in or out. It's random. But in this online survey stuff, we don't know it's a random or not. We could repeat the whole event, and the exact same number of people will be reporting or not reporting. Okay, so I'm not going to treat R as random. But here's the magic part, that even nothing's random, I can still use probability theory. Because take a look at these averages. This is average in the population, and this is essentially the sample mean, right? If I put R equal to 1, if the value is reported. If it's not reported, R is 0, so I don't need to know this value, okay? So the sample average I'm putting together is simply, okay, now this is don't get too intimidated by this formula because it's really quite simple. All right, so mu G here is the population average, and the mu G hat, a statistician like put a hat there. Hat means an estimator, okay? That is just a sample average, okay? Now, if I take, remember, this is the average of n value divided by n. Now, you can think about this I, the index, is a random variable taking value from 1 to n, and each with one probability 1 over n. It's a uniform on these integers, okay? Then the average of that integer, the g, is simply the expectation. For those who are taking statistics, right? This is just a fancy notation to write as expectation. The average is just the average of each individual, but since we're here, we divide by 1 of n, everybody is equal chance, okay? Why do I write this way? Why do I make the life much more complicated? Is because I want to get the index right. So if you write this way, it turn out to be, this will be just the average of all the g's. And this part, the numerator is the expectation of r times g, right? And the denominator NR. NR is just the average of the sum of the r's, how many people responded. So if you divide by n, both sides divide by n, so you get this expectation of the product divided by the expectation of r itself. Why do we write this? For those who you study statistics, you may remember, if I take a common denominator, the top will become the expectation of the product minus the product of expectation, okay? The average of product minus the product of average. And for those of you still remember, that is called a covariance. That says how the R and X covary, okay? If you then from the covariance, you can divide that by the standard deviation of R, standard deviation G, then you get the correlation. And because, it's slightly technical, because R is 0, 1, the variance of the R is some of you may still remember, is 1 minus P times P. P here is FR. So, and this is the standard errors of the G in the population. So why do I write this simple difference into these three quantities? And that's the key message I want to tell you is incredibly important. Okay, so what is this quantity? This quantity is the correlation, simple correlation, between the value will be reported and whether the probability that person reports, okay? So all the bias comes from the following phenomena, right? Why a sample will be biased? Well, imagine that if, let's say, this was the income. If you have high income, you tend to not reporting, you know that will be correlated, right? Your behavior reporting is determined by the value, right? So that will cause the bias. If everybody, what does simple random sample do? Simple random sample is simply say whether you report or not is not determined by your value. It's by the mechanism I give to you. Therefore, that's uncorrelated, right? So you will see that as long as if this thing is 0, if the perfect is 0, then you will have no errors whatsoever. Okay? So this row is what I've been looking for. That is the quality index. Okay? The quality index here is a simple correlation between the value you want to collect, let's say 0, 1s or income, and the people's reporting behavior or recording behavior. Okay? So the simple random sample, the reason simple random sample is so good is because by introducing this random calculation, this value tend to be very small. In fact, practically is 0. What is this quantity? This is the index for quantity. This is the fraction in the population. Okay? So this one can go to 0 only if you take the whole 100%. So what happened is, this is the traditional sort of statistical way of control the error. This essentially is a big data is trying to control. Big data say, oh, I'm going to control the error by having the sample size very, very large. Okay? Unfortunately, it takes a lot more to make this thing small than make this thing small. And then what's the last part? Last part is simply say, what's the variance? How spread is this G function in the population? And that is essentially the difficulty of the problem. If everybody has the same value, this G will be 0. The sigma G will be 0. Sigma G is the standard errors. okay? So you see, if people's opinion vary a lot, that's much harder to estimate. You need more people. If everybody has same opinion, you just need a few people, okay? So essentially, you have three quantities. Essentially, the difference, which is called the mean square error between these two quantities, are controlled by three quantities and only three quantities: the quality index, the quantity index, and the difficulty of the problem. Got it? This is what I mean by formulating this problem. And it turned out that if you want to reduce your error, there are three ways you can reduce it, okay? One is by doing statistical probability sample for which the responsive behavior will be completely independent of what you report. Now, if you do simple random sample and everybody follows what you ask them to do, this will be effectively zero. But unfortunately, even if you do simple random sample, if people choose to not reporting, it will destroy this correlation as well. It will actually make them large as well, okay? So this is the hardest part. This essentially is most of the statistics these days we do, trying to eliminate the confounding factors, trying to stratify, trying to do all sorts of things to reduce this. Big data can help by reduce this. But I'm going to show you in a minute by looking at the data, give a specific example to emphasize. We have, collectively, we really have overemphasized this row. It's very hard. If this guy is not zero, it's very hard to bring this thing down because this, okay? Because this is a big number, all right, compared to this. And of course, there are the other way to make problem simple. Choose a simple problem to work on. Now, so that's not very much under your control. Now, you could control that if you do statistics called a stratify. Instead of trying to study the whole population, you separate the male and the female, Democratic with Republican. If you have all these party informations, then you estimate according to each subsample, the sigma within each subsample more homogeneous, the sigma will be small, then you combine the answer. So there's another way to use this, okay? So basically what I'm telling you is that if you understand this formula, you understand pretty much like 80%, 90% of statistics, okay? So even if you have only taken one course, that if you really understand quality, quantity, and the difficulty, these are the three things, okay? And you can't really have all these. I mean, of course, ideally you want a problem which high quality, high quantity, low difficulty. In real life, things does not happen that way. I'll put it differently. If that happened, the problem does not require you to solve it. Somebody else has already solved it. Okay, so you always have to choose one of those things to work on. So now I have preached enough. I want to now give you a specific example to show you how these numbers really convey the message. Okay, now here's a slightly technical part, but bear with me. Remember here, I said there's, if I do mean square error, I put the square, so there's square here. And here's what happens with the statistical calculation. If you have a single random sample, you can show the following. And this part is interesting. This part, even for professional statisticians, we don't do that calculation. On average, if I choose everyone randomly answer, the expectation is 0. So the bias part is 0. The variance part, that turned out to be a little bit surprising. The variance part of that correlation, average over variance calculated according to the simple random sampling, is 1 over capital N minus 1. Capital N here is the population size. So that number is essentially 0. And the most remarkable one, that correlation does not even depend on the G. Does not depend on what function I choose. So what that shows is simple random sample is a way to get rid of lots of bias very, very effectively. Now, the way I explain to people is that people say, well, how could it possible that you choose, say, in the United States, right? You have about 320 million people. Let's say you take a sample, say 500 people. No, let's say 5,000 people. If I move to China, China has about 1.4 billion people. I'll be asked a question like, how many sample size I need in China in order to maintain the same accuracy? It turned out the answer is still 5,000, right? And that people always say, well, that's completely counterintuitive. Well, it's not, because there's an assumption here. The assumption is it's a simple random sample. You mixed well. The analogy I was given, and particularly for the Chinese audience, is think about you are asked to taste how salty your soup is. If you have a bowl of soup, right, all you need, if you mix them well, you just need a tiny spoon. If you have a big bucket of soup, if you mix them well, you only need 1 spoon. It doesn't matter how large this is, right? But if you don't mix well, then the size of the container is important. The big data is trying to test the saltiness, not by mixing them, because they don't know how, by trying to test as much as possible. Now you see the problem. Okay? If you test out of enough time, you'll be dead, right? There's just too much of things. So I'm going to show you how bad it is, right? So for simple random sample, because this guy is 0, so eventually this is the standard formula. Remember, it's the sigma squared divided by n. So this is what's interesting, that in the simple random sample case, we have taught all of you, if you take a statistic, say, don't worry about the population size, only worry about your sample size. That is what makes possible to do all the social science studies, right? You survey 500 people, survey 5,000 people, you can study the whole population, okay? Unfortunately, that is gone. Once it become big data, if it's self-report, if this guy is not 0, then you can see this can't go to 0 unless FR goes to 1. Now you get stuck. For this guy, this one was 0. On average, the correlation is 0. Now I'll show you how bad it is, okay? So you can actually do the following calculation. Again, this formula looks complicated. You can do the following calculation. You can ask yourself, suppose I have, say, 50% of my population, okay? Let's say United States. That's 160 million people, right? Suppose I know what this correlation is. What is the corresponding size of a simple random sample will produce the same error? Okay? You can ask that question. So there is, if you equate them, you can come up with this thing called effective sample size. Now, the formula is a little bit complicated. Let me just plug in some numbers to show you what that means. So this row here, which is the correlation between the reporting behavior and the value you want to record, is what I call the data defect index, because the higher the number, the lower quality of the data is. Okay? Now, imagine the following. This is a correlation, right? Correlation is between minus and 1, okay? Let's assume that correlation is 0.05, 5%. Now, how many of you think that's pretty large or think that's pretty small? 0 means there's no correlation, okay? Let's say I say there's a 5% correlation, 0.05. For many of you know, if you get a 5% in many things, like you consider that's pretty small, right? But it's going to kill you. I'm going to show you what happens. If you have a 5% correlation, if you have 50% of the population, which is what? Which is 160 million, the effective samples that you plug in is about 400. So what I mean is the following, okay? You have the half of the US population. If their reporting behavior is slightly correlated with what they're reporting, and the correlation is measured by 5%, how much errors you can produce from that data set is equivalent to you do a simple random sampling, everybody report honestly, 400 people. That's the equivalence. 160 million is equivalent to 400. Why? Because for the simple random sampling, is the sample size matters. For the other, is this fraction matters. 50% is not a large fraction. And the 50% of the United population is 160 million. Now, when I've given talk at the Seattle, I told people, like, you may say, wait a minute, this seems so striking. I said, well, I can make it even more striking if we go to China. Suppose Donald Trump trying to be the president of China. 50% of the Chinese population is 700 million, right? At least officially, 700 million, right? You see the number will be humongous. The problem is you run into trouble. You run into what trouble? It's no longer just the sample size matters. Once you lose control of the quality, the population size comes in. Okay? After I surprised myself doing this calculation, because I said, well, 5% seems very tiny. Until you look back, you will see why that's a problem. You see, simple random sampling control the correlation on the order of 1 over capital N. It's on the population size. Okay? So 0.05 is actually very large. 0.05 is 1 over 200, right? So so lesson one. Lesson one, what matters is the quality, not much the size. Got it? Okay. Second is you need to watch the relative side. When people say big data, you say, okay, tell me what do you mean by big? Is a big fraction or a big absolute size? Okay? 50 million means nothing if the whole population is trillion, right? It's absolutely nothing, right? And people tend to be impressed by the absolute size. Okay, I'll show you. And the probably most important lesson to learn is don't ignore the seemingly very small data set with good quality. People, you see, the problem I did is like when you have a 50 million, if you have another data set with 500, most people would say, well, forget that 500. Why bother? If you do some weighting, it's complete gone. But what I just show you is probably all the information is in that 500, if you can trust the quality, okay? So what do I mean by big data paradox? Well, this is what I mean by that. Okay, imagine this, right? Now, this is slightly technical, but I want to, again, tell you, because the difference between them is the effective sample size is much, much smaller than the reported size. You know how we do these confidence interval? This confidence interval is always the error, so the estimated plus minus 2 standard deviations. But because this error was so grossly underestimated, whenever people just mindlessly using the statistical formula, say plug in the sample size 50 million or 160 million, they get the interval is completely tiny, right? Remember the bar at the very beginning? If you use the wrong size, not use the real independent size, use this sort of, this bars you will be seeing completely tiny, right? So what happened to me is this is what I've been calling, so basically saying, instead of in this particular case, right, if you want to get it right, you need to choose the C. People tend to like 2 plus minus 2 standard errors, or at most people do 6. Remember 6 sigma? You may have heard that. Nobody does more than 6, right? 6 is already like 99.999 saying. But in this case, if you really want to get it right, you need to do 600. Just because you completely screwed up this denominator, right? And basically, so this is what I've been calling paradox, the big data paradox, because the bigger the data, the more certain you will miss it, right? Because you sent it at the wrong place, okay? And your interval is so tiny. Remember the curve I produced at the very beginning? I give you this large bar, right? If I give you this tiny, tiny bar, what do you think? Oh, you think my estimate is so precise. I don't have to worry about the bar. Well, only if the bar was calculated correctly. And the big data, if you don't know the quality issue, if you do not take into the quality index, you're going to use the sample size 160 million or 50 million or whatever you do. And once you plug in that sample size, all the bars will be essentially 0. So you'll be, I'm done. Well, you are done, but you might be completely wrong, right? Okay. So let me now get to the second point. Now, some of you may say, well, Xiao-Li, you're talking about something may or may not be important, because most time people use this big data is not necessarily about estimating the population quantity. What I'm talking about so far is about estimating population quantity, right? And people, there's a large a team, research there, are working on the following problem, which is called individualization. So here's what the big data promise, right? The big data sort of like, remember these days, people can trace a lot of things you do, right? Whatever you're working on, your iPhone, your search behaviors, all the things, there are lots of data about you. So people think that we can get to personalized medicine, you have to personalize education, personalize the news, personalize marketing. This is very annoying, right? Anytime you do an email, there's some advertisement there, sort of trying to detect what you're doing, right? Okay. But statistically speaking, there's something interesting, right? So what's the gift about the big data? The big data gift here is to say we can study about you by looking at many people just like you. The real problem is no one is exactly like me. I hope not, right? Each of us is unique, okay? So the question then is, what are we really talking about? When we talk about statistical evidence of personalized treatment, what are we really talking about? Most treatment you get, if you ever take any medications, these medications are approved, for example, by FDA, United States Food and Drug Administration, right? What do? How do they approve things? They do clinical trials, right? They have two drugs. Typically, one is a sugar pill, the placebo, the other is real treatment. Or maybe one standard treatment, another is a newer drug. They give two groups of people, right? Follow them for months. Then they do some analysis. Basically, in the end, they say, this group, 50% survive, this group, 20% survive, therefore this is better, right? Okay. But 50% is about the population. It says nothing about you. Well, it says something about you, right? But not much. What if I'm the ones belong to the other 50%? Even it's 95% of success rate, what about me being for the 5%? Would that work at all, right? So now, when I start thinking about this problem, I ask myself, what do we mean by statistical evidence of an individual? Because there's not any data, right? Okay. Now, I'm going to give you the following example. On the surface, that seems has nothing to do with big data at all, but I'm going to explain to you what this problem is. Suppose you suffer kidney stones. How many of you have suffered kidney stones? Me? Oh, I'm lucky one. Kidney stone is extremely painful, okay? Imagine Mr. Payne has a large stone, and he wants to be treated. There are two treatments, okay? This was a study published in this journal, British Medical Journal, many years ago. Well, actually, this is now 30 years ago. If you only read the abstract, papers come with abstract text, right? If you only read the abstract, because you are having pain, you're only reading the abstract, you will find in the abstract there are two treatments, treatment A and treatment B. And treatment B has 83% success rate, and treatment A has 78% success rate. If that's all the information you have, which treatment will you take? B, right? Agree? Depends. Smart. Someone learned. Well, but if all the information, if this is all the information you have, and then you say you're going to take A, if not taking B, then I would say the stone is not in your kidney, but in your brain. But if you read the whole article, inside the article somewhere, it divides the stones into large size and a small size. Then suddenly, regardless you have a small stone, you have a large stone, the treatment A is better. Now which one are you going to take? If it's a small stone, you take A, and a small stone, take a large stone, right? This is something, by the way, this is called the Simpson's paradox. This can confuse a lot of people, right? What happened? Well, it's very important. This is a little bit of statistics here, okay? So far, you see, I have not done any calculus, right? These are all simple arithmetic. Look at these. This is very important that I present you all the fractions. If I only give you these percentages, you say, well, you did some mathematical arithmetic errors, okay? Look at the data. 263 plus 87 is 350. 80 plus 270 is 350, right? There's no sleight of hand. Everything's correct. Okay. Now I want to ask some students, what happened here? Why is this happening? If you put them all together, you will say B better. If you separate, suddenly A is better on every single subset. Yeah, go. Tell me. What's the reason? If you look at the data. They're different weighted, okay? But that does not necessarily explaining why this is happening, right?
I think for small stone, probably doctors retreatment.
You're exactly right. What happened here is the following. If you look at data like this, you should be able to tell this is not a clinical trial. These are actually, they put 350, 350, trying to sort of make them equal, but that's the quantity issue. It's not a quality issue, right? I'll keep asking, keep emphasizing the quality issue. What happened here is you clearly see the doctors treating large stones more use A than using B, right? You see, when you do clinical trial, how do you do it? You flip a coin, random assigning them to the treatment. When you go to see a doctor, if the doctor has any training, he or she is not going to flip a coin, right? You don't like, say, flip a coin. Give me the treatment, right? Now, for this study, we wish they actually flipped the coin, but they won't, right? So you can see this clearly, there was a confounding factor. Which treatment they receive depends on the severity of the disease, the size of the stone. This is exactly the correlation. What answer they give correlated their reporting behavior. Okay? Think about R is the reporting behavior, is the recording behavior. That's exactly, it's that correlation destroys things. Okay? So what happened here is that actually I can tell you what these things are. A is open surgery. As you can see, when the stone size is too large, the doctors say, let's have a surgery, take it out. That's success rate high. B is this unpronounceable treatment. I'm not going to pronounce it. I don't know how anybody want to pronounce this. What's so scary is this article is to promote this as a non-invasive surgery. You see here's the problem. Most doctors, or probably all of them, only read the abstract. If the abstract gives you a high success rate, non-invasive, don't you think you're going to get it? Who's going to give you lower success rate and more invasive, right? Until you look at this, right? So this is a great example showing how can easily statistics can mislead you if you didn't read it right, okay? What's important here, let's have a little bit of notation. The Y here, let's say there are two outcome variables, okay? The one outcome, sorry. Y is cured or not cured. Think about that previously you vote for Donald Trump or not vote Donald Trump. X here is the stone size. What's important here is the stone size here is the pre-treatment stone size, okay? These are stone size before the treatment, all right? So the reason I want to emphasize, in a minute you will know. But here, first there is a tough question. Now, and I want to emphasize, so far you say, well, what this has anything to do with big data or personalized medicine because it seems a very small, small data set. Well, here's what's being personalized. Remember Mr. Payne, the patient? We know his size is large. That is one piece of personal information. I can ignore that information. If I completely ignore that information, then if this is a clinical trial, I will be using this information, right? So then the thing says that, like, if I know this person has a stone size, then I should go one deep. Now I can start collecting more information about that individual. And then here you immediately run into the following problem. Well, we know that in this case, this does not seem to make any sense because these groups are really apples, oranges. These are not really comparable. By the stone, they seem better. But how do I know that if I further divide them, for example, stones still have different type, not just a size, has a different chemical component. Well, how do I know that if I divide further by stone type or even by surgeon's skill, that these results will not flip? And that's where the individualized inference come in. The individualization is about collecting more and more about you, right? Anytime I collect something about you, let's say your age, then I'm going to compare you with all the people with your age. Then I say, no, that's too big a group. Let's compare people with your age and your gender, because then you shrink the group, okay? They say, no, that's not enough. Your blood pressure, smaller group, right? Anytime you're compared to that reference group, how do I know these answers do not change? And in reality, they do change. More importantly, where do I stop? Right? Okay? So I want you to keep it in mind. So now let me make the problem. This is known as the Simpson paradox. Let me make the problem a little bit harder for you. Okay? Pay attention to this one. Okay? The previous one, probably most of you would agree that using stone size is a better answer than aggregate. Okay? But now let me make this problem a little bit harder. It's exactly the same data set. I'm using a data set. But let's say it's for not treating the kidney stone, but rather for relieving the pain. Okay? And this time, the stone size is post-treatment. Suppose you take medication to control the pain, but they did not measure your stone size. They measure your stone size after you take medication. Is that clear? So that your medication may affect the stone size. May or may not. We don't know. Okay? So as I said, now Y indicates the pain relief or not. And X indicates the post-treatment stone size. And we have the following assumption. The treatment A is a control treatment and known to have no effect on the size. For example, Tylenol. Okay? You take the painkiller, and we know that drug does nothing to the stone size. Okay? But we don't know about the treatment B. Treatment B may or may not have effect on stone size. In reality, probably take a few times the drug is not going to change the stone size. But let's just, for the sake of argument, let's say there are some wonder drugs that make your stone size shrink or enlarge. Now, I'm going to ask you the question. Now, imagine this is a clinical trial. Okay? I randomly assign 350 people to one group, 350 to the other group, and then I report this data set. Exactly the same data set. The meaning is different. The stone size now is post-treatment, and the outcome here is whether you have pain or not. Now I want to ask you, suppose you have a large stone size. Okay? People take X-ray. You need to take a painkiller. Which one are you going to take now? A or B? A little bit harder problem, right? This is all the data you have, okay? How many of you will take B? 2, 3, 4, 5. Okay, there are a few of them. How many of you will take A? Now this time there's no depends answer because the pain is in your body. You're suffering. You have to take one. Okay? You can say it depends, and the stone is you're still in pain, right? Okay. Now if I force you to take one, how many vote for B? Okay, about 20%. How many vote for A? The rest of you, what do? Huh? You take a both. That's a creative answer. Okay. That's not a bad answer, actually, really. Well, in this particular case, if you ignore the size of your stone, then taking B is the correct answer. This is a clinical trial. If I don't use the people who have the same large stone, just treat myself, ignore my personal information, I'm just one of the population, right? So I'm going to take the B. Now, this may or may not work for you, okay? So the problem is, well, people say, wait a minute, I do know my size of stone. I should take this one because this is better than this. But you have a trouble here. The trouble is, for those people, you want to compare yourself to all the people who have large size before the treatment. These are the ones you comparable. This is the correct answer because these people, we tell you A does not affect the size, okay? The trouble is you don't know about these people. These have large stones here, right? You don't know whether that size stone is large, is pre-treatment or post-treatment. Is that clear? Now, in reality, probably really it probably does not really happen, but just for the sake of argument, comparing this one is a little bit problematic because these are not comparable group, okay? So this is what I'll be talking about, this idea of resolution. I call multi-resolution. The idea of resolution here is anytime I use a personal information, it's like a zoom in. You get a more refined look at you, right? So this is resolution 0. completely ignore any information about you. You're just a patient. For the resolution 0, we will use the treatment B, okay? No controversy here, because I told you that's a clinical trial. You could do resolution 1, right? Resolution 1 is I look at one piece of information, the size of stone. The trouble with that is this one you can trust, this one you cannot trust. Okay? So now let me give you an answer. Make us a following suggestion. See how many of you like this answer. I'm going to reason in the following way. I'm going to say, okay, I have large stone, right? If I take a treatment A, I know the success rate is about 73%. And the treatment A. That's the information is reliable. And the treatment B, I can't trust this because I don't know what this is, right? And I don't have any information about what will be the success rate for people suffer large stones and the treatment B. But if I ignore the size information, I know the success rate is here, right? So what about I do this diagonal one, right? What about I use the personal information and the one treatment, but I don't use it in the other? Can I do that? If I do that, I will see, I still will take a B because this is 83% versus 73%, okay? So I'm going to ask a question for you now. How many of you like this answer? Raise your hand. How many of you say, oh, this is completely unreliable because you're comparing two different things? I guess everybody falling asleep. Well, how many of you say the answer depends? No, you can't even say answer depends. Yes, you. Well, actually, this is a part of that actually is a little bit controversial because you are sort of in a way compare apples and oranges. It turned out to be there are conditions under which this will be correct. Because of time, I'm going to show you this diagram. Okay, then I got to stop there. I'm going to just skip these. So what's important here is this. Y is the outcome, right? Think about this. This is a particular individual. This is like and the treatment A. And I want to compare. This is me. I want to find all the people I can compare it to. But I only have the peoples who get treatment A, because each person can only get treatment A or get treatment B. They cannot get both, right? So for this group, I can estimate its average by using all the people who have treatment A. And for this one, what I want to compare are the peoples who I want to compare all these individuals, how they differ when they take treatment A versus take treatment B, okay? But I can never implement both on the same person, right? Okay, so although this is what I want to compare, I cannot really directly do this. But what I can is I can find a group of people, they will enter treatment B. I find a group of people, they will enter treatment A. The problem is these, in the population, you see, they're exactly identical. It's the same group of people I want to compare. In real life, I can only, for one group, I can treatment A, one group of treatment B. Okay? Therefore, my estimator here will be biased. But this is a case where the difference, the cross one, and the certain condition, which I don't have time to explain, that is actually a better answer because it has a smaller mean square error. So what do I mean by that? So here is the real issues dealing with these problems. Anytime when I try to match more and more people, I am making my inference more and more relevant for me because these people are more and more look like me, okay? It's just like, I make them, this is all treatment B, but I want them to have people both A and B, and that'll be more relevant. But the problem is the more relevant population gets what? Smaller. You know what happens when the sample size is smaller? The statistical error goes up. The bias goes down. The variance goes up. In order to control the variance, the random error, I need to make the population large. But if you make that large, that becomes less relevant for me. So fundamentally, this is just a classical bias-variance trade-off. Bias is a systematic error. Variance is a random error.
Sample size controls the random error. Matching controls the systematic error. There's no way to get out of this. The God creates rules like this. If you want people to be more and more relevant to you, in fact, even if you have a twin brother or twin sister, you don't even have a perfect match, right? And that's not even sample size 1. That's only sample size half, because your twin brother, unless you have 2, your twin brother can only take one treatment. You see what I'm saying? Okay. So this is a fundamental problem. It's a bias-variance trade-off. The whole question about, remember I said what resolution you should stop, right? Is really, you want to stop at the level where there's still enough sample size to control the statistical error, but it's relevant enough to you. That is where the big data really pays off. Because the big data allows to find people reasonably match you and still have enough sample size. And that's where the really the big advantage of the big data. But you have to be very careful how to do that matching. Okay? Traditional data set just not have enough to do that kind of controlling. So for the individualized methods, individual treatment, the big data, yes, it's possible, but the key is really this idea of doing matching. Now, matching is a simple idea. There are all sorts of ways of building model, but whatever it is this fundamental trade-off. You call it, what I've been calling it is the robustness versus relevance. Relevance means how relevant to you. Robustness is how stable the answer is. You can make the answer very stable, but it may not apply to population, but may not be relevant for you. Or you can make the statement very relevant to you, but it's just like based on a few people, there's so much fluctuation. And because that fundamental trade-off make a lot of these studies are really very difficult, but that's also great news for all the statisticians, for all of you, because you always have a job. Thank you very much.